Hello student. So far we have discussed how to find magnetic field strength by using Biot-Savart law and application of Biot-Savart law. Clear? Now we will discuss the Ampere's law to determination of magnetic field when there is a current flowing through the conductor. Clear? This is important law to determination of magnetic field. So according to this law, this is known as Ampere's law. According to this law, you can write this first statement. According to this law, the line integral of magnetic field, the line integral of magnetic field for a closed loop is equal to epsilon naught mu naught times total current within the loop. This is the statement of Ampere's circuital law, or the statement is known as Ampere's circuital law. According to this statement or according to this law, the line integral of magnetic field for a closed loop or any circular loop is equal to the mu naught times total is equal to mu naught times the total current within the loop. This is the statement of Ampere's circuital law, and its mathematical formula can be write, that is B dot dl over line integral, which is equal to mu naught times total charge in means enclosed within the surface. What is B dot dl? This is length element. This is called line integral, and this circle indicate the closed loop. That means total magnetic field within a closed loop, which is equal to mu naught times total current within that loop. This is law. This is important law, and this is the mathematical formula of Ampere's circuital law. By using this law, we can find magnetic field for a conductor. Clear? So this law, what is I in and what is B and what is dl? You know what is mu naught? Mu naught means where mu naught equal to absolute permeability in free space. Clear? Absolute permeability in free space. What is I in? I in means total current within the closed loop. Suppose Ampere's circuital law. Suppose there are number of conductor. Suppose this is I1 and another conductor, current flowing through the conductor I2, another one conductor I3, and another one conductor, that is I4. What does it mean? This cross indicates that the direction of current which is inward direction are perpendicular to this plane, and this cross also indicates same, and this dot indicates that the direction of current which is outward direction and perpendicular to this plane. But its magnitude, that is I1, I2, and here I3 and here I4. The current flowing through the conductor is not same, it's not equal. There are different current conductor, different magnitude of current flowing through the conductor. This dot indicate that. We know what does it mean. That means this is the inward direction I, and this indicate that the direction of current which is inward direction and perpendicular to this plane. But this dot indicate that the direction of current which is outer direction and perpendicular to this plane. So what is mathematical formula of Ampere's second law? That is B dot dl over closed integral, that is mu naught times I enclosed. Mu naught times I in or I enclosed. So first we have to know what is I enclosed. I enclosed means suppose first we have to know, we know from electric field what is Gauss law. Gauss law means E dot dA over surface integral, which is equal to Q enclosed by 1 by epsilon naught time Q inside. This is Gauss law in electrostatic. Clear? And in Gauss law we deals with the Gaussian surface. But here this is Ampere's second law, we deals here the Amperian law or Ampere's law. Surface and law. What the difference between surface and law? Surface means suppose we have a sphere. If we imagine a Gaussian surface, then the Gaussian surface like an area. But in this case, the Amperian law, this is only a law. Suppose one example, there is a circle. This is circle and there is a cuboid. Which is low and which is surface. This is low and this is surface. Clear? So in electrostatic we deals with the Gaussian surface, but in this case Ampere's second law we deals with the law only. That means circle only. Clear? So first we have to draw a imaginary loop or Ampere's loop, called Ampere's loop. Suppose there is an Ampere's loop and this loop is known as imaginary loop and called Ampere's loop or Amperian loop. Clear? Now look at the formula B dot dl, which is equal to mu naught times I enclosed. What is B? B means total magnetic field due to total current flowing through the conductor. That means this is Amperian law. So this magnetic field due to this current, due to this current, due to this current and due to this current. Clear? So this B, that means B net. We can write B means B net, net magnetic field due to all the current flowing through the conductor, not inside the Gaussian surface. This is not inside the Amperian law. This B, which is known as B net. Clear? This B, which is known as B net. That means due to total current flowing through the conductor. Clear? So we can write this is B net. Next, what is I enclosed? I enclosed means we deals only with the current flowing through inside the Gaussian loop or within the Gaussian loop. Suppose this is Gaussian loop. This is Gaussian loop. So I enclosed equal to total current, this current. That means I1 and I2. Clear? Suppose we imagine that this is a loop and this loop is known as Gaussian loop, and the Gaussian loop, imagine this direction. This is the direction of Gaussian loop, because Gaussian loop is imaginary loop, so we can take or we can imagine the direction. This is the direction of Gaussian loop. Clear? If this is the direction of Gaussian loop, suppose this is the direction of magnetic field, net magnetic field B net. if you choose a small element dl, if this is the direction of net magnetic field B net, then what the direction of what is I enclosed? I enclosed means I1 which is inward direction and I2 which is outward direction. Clear? We know that if there is a current carrying conductor and current flowing through the conductor I, then by using right hand thumb rule, we can find the direction of magnetic field at a distance d, and we can find the magnetic field at point P due to this current or due to this conductor. That means the thumb indicates the direction of current and the point P which show the direction of magnetic field. That means this is the direction of magnetic field which is inward direction. Clear? And this is the direction of magnetic field which is inward, and this is the direction of magnetic field which is at point B which is outer direction, but at point P which is inward direction, and at point B the magnetic field which is outward direction. Clear? And the magnetic field always make a concentric circular loop like this. This is the magnetic lines and this is the current carrying conductor. Clear? If there is a current in this direction, then magnetic field inward direction, but at this point magnetic field which is outward direction. If we imagine this is the direction of magnetic field, this is the direction of magnetic field which is inward direction. Clear? If this is the direction of magnetic field which is upward direction, this is the direction of magnetic field, then the current, the net current must be which is outward direction. But there is two type of current, one going through inward direction, one going through outward direction. So we can write I enclosed. I enclosed means total current within the Amperian loop, because this is the direction of magnetic field which is outward. So if this is the direction of magnetic field, the tips of the finger which indicate the direction of magnetic field, then the thumb indicate the direction of current. So the net current within the Amperian loop which is coming outward. So I enclosed can be write that is I2 minus I1. Why? Because this is the direction of current which is inward direction and I2 which is outward direction. Clear? If we take I2 is positive direction and then I1 which is negative direction, there is two type of current which is coming inward, which is coming outward. Clear? So net current within the loop which is equal to I2 minus I1, because this is the direction of magnetic field. Clear? Suppose if we take the direction of magnetic field in downward direction, this is the direction of magnetic field. Clear? Then what is the net or I enclosed? But in this case I enclosed which is equal to, for this I enclosed equal to I1 minus I2. This is net current. Why? Because this is the direction of magnetic field which is inward direction and this is direction of magnetic field which is outward direction. But in this case the direction of magnetic field which is downward, so this is the downward direction. Clear? And the net current which is flowing through inward direction. So this current must be greater than this current. So you can write I1 minus I2. Clear? This is all about Ampere's law or Ampere's circuital law. Clear? This is the mathematical formula, and this law which is just equal to Gaussian law or Gauss law in electrostatic. Clear? So again we can write closed integral, that is B dot dl which is equal to mu naught into I enclosed. That means first we have to draw a Amperian surface, and what is I enclosed? I enclosed means total, suppose this is amperian law, and there is I1 which is outward direction outward, there is I2 which is also outward direction, I3 which is also outward direction. Clear? So in this case I and those can be right I1 plus I2 plus I3 because these are only one direction. These are coming outward direction. Clear? And B equal to, what is B? B means B net. Suppose there is another conductor I4 which is inward, I5 which is outward. Clear? So what is B? Or this is called B net. B net means due to I1, I2, I3, I4 and I5. All the current inside and outside the amperian loop, not inside the amperian loop. Clear? So B net, which is due to all the current inside the amperian loop and its periphery current. Clear? But I enclosed equal to within the amperian loop. Clear? This is all about Ampere's law. Now this law can be proved. Actually law cannot be proved, but here this law can be derived, or this law can be proved from long infinite state conductor or infinite state conductor. Clear? How? Suppose we have a long infinite state conductor. This is infinite conductor, and suppose this distance is R and this point is P. We know at this point, if this is infinite plus infinite and this is minus infinite, and B equal to mu naught by 4 pi I by R. This is perpendicular distance at point P, and sin phi 1 plus sin phi 2. This is this is finite length, then this angle phi 1 and this angle phi 2 we have discussed previous classes. What is phi 1 and phi 2? For infinite long state conductor, phi 1 and phi 2, we can write the formula. What is the formula? That is B equal to mu naught by 4 pi I by D, that means current flowing through I, and which is equal to, this distance was D, and sin phi 1 plus sin phi 2 for finite length. If this angle phi 1 and if this angle phi 2, this is the mathematical formula. B due to the current carrying conductor, that means from A to B. Here suppose we have a infinite long state conductor. For infinite conductor, the formula can be written. This is plus infinite, this is minus infinite, and this distance is at this point P. But here for infinite length, that means phi 1 equal to 90 degree and phi 2 equal to 90 degree. Clear? So this relation term to be the B equal to mu naught by 4 pi I by D sin 90 plus sin 90 equal to 1. So 1 and 2, this is 2, and which is equal to B equal to 2 to the 4. So mu naught I, that is mu naught I by 2 pi D. This is the mathematical formula of magnetic field strength due to an infinite conductor. Clear? This is equation 1. Okay. Now we'll come. This is the mathematical formula for long state conductor, and if current flowing through the conductor I, and B equal to mu naught I by 2 pi D. Clear? So this is the direction of flow of current for an infinite long state conductor. We know if this is the direction of flow of current, then the magnetic lines are always concentric circle around the conductor. Suppose this is the direction of current and this is the direction of magnetic lines. That means this is the direction of magnetic field lines, and these are concentric. So if we draw, we have to find magnetic field at point P. That means this is the mathematical formula B equal to mu naught by 2 pi I by D for infinite long straight conductor. And if we choose the small element dl, this is dl, and if we draw a Amperian loop in this way along the direction of B, that means what is Amperian loop? What is the significance of Amperian loop? If we draw a Amperian loop at any point, if we draw a Amperian loop through this point, then Amperian loop indicate the symmetry of magnetic field and theta. That means at this point the magnetic field which is in this way, that means inward direction, and this point which is outer direction, and this point, because if there is a current carrying conductor and current flowing through inward direction, due to the right hand thumb rule, the direction of flow of current in this way, and this is the direction of flow of current which is at point, this distance is r, and this distance is r, this distance is r, and this distance is r. So at this point the magnetic field downward direction, and this point in this way, and this point this direction the magnetic field, and this point is the direction of magnetic field. Clear? But direction are not equal. What is magnitude? What is magnitude means B equal to mu naught by 2 pi I by D. If this conductor is infinite, then the magnetic field at this point, this point, and this point are equal. Clear? So we have to draw a Amperian loop. What is Amperian loop? Amperian loop means it indicates the symmetry of magnetic field. If you draw a Amperian loop over the magnetic lines, this is the Amperian loop. This is Amperian loop, or this is closed loop. Clear? Which is over the magnetic lines. Clear? But if you choose this point, then this is the direction of dl length element, because we chose the direction of Amperian loop in this way along the direction of magnetic field. So this is the direction of magnetic lines, and this is the direction of Ampere's law. Clear? And this is the length element dl. So this is the direction of dl, and this is the direction of magnetic field. If you choose magnetic field strength here, and here, these 4 points, the strength of magnetic field are equal. That means Amperian loop indicate the symmetry of magnetic field. That means here, and here, magnetic field are equal. And if you choose the angle, what is angle? That means we have Amperian, or we have, that is B dot dl close integral equal to mu naught times I enclosed. This is LHS. So LHS equal to B dot dl, which is equal to close integral over B dot dl A dot B, which is equal to B dl cos theta. What is theta? Theta is angle between magnetic field and d element. So this Amperian loop, or this is Amperian loop. This Amperian loop gives symmetry of magnetic field. So these 4 point magnetic field equal, and this is the length element in this direction and magnetic field in this direction. So this point theta equal to 0 degree. If you choose this point, this is the direction of magnetic field, and this is the direction of length element. So here also theta 0 degree, and here also theta 0 degree, and here also theta 0 degree. So Amperian loop gives the symmetry of magnetic field and theta. Similarly, if you chose a small element, length element dl here, then this is the direction of magnetic field, and we chose along the direction of magnetic field, we chose the direction of Amperian loop also here, so that the angle at this point theta equal to 0 degree. If you choose another one, this is the direction of dl element, so here theta equal to 0 degree. If you choose another element, the direction of magnetic field, and this is direction of dl element, so here theta also 0 degree. If you choose another element, this is the direction of magnetic field, and this is the direction of length element, so here also theta equal to 0 degree. Clear? So we can write B dot dl cos theta, but B is constant. This point B is constant, which is equal to mu naught I by 2 pi d. So we can take constant quantity, that is B close integral, that is dl, or B dl cos theta. Cos theta means theta is here 0 degree everywhere. So you can write dl, since cos 0 degree equal to 1. Next, what is DL? Suppose this is DL element, DL, and total length will be 0 to 2 pi r, total circumference. So, which is equal to B into DL integral, which you can write, this is L and lower limit 0 to 2 pi r. Clear? Now, we can write LHS, that is B dot DL, which is equal to, first we have to use upper limit, that is B into 2 pi r, which is equal to, what is B? B means magnetic field strength mu naught I by 2 pi d. So, mu naught I by 2 pi d. D means here r. So, you can write this is r and this is r into, it is 2 pi r. 2 pi r cancel, which is equal to mu naught I. And this is RHS. Because this is the current which is inside the ampere loop. So there is only one current and direction of current in this way. So this is mu naught I. This is RHS, which is proved for ampere circuital voltage V dot DL, which is equal to mu naught I. The mathematical formula of ampere circuital law. Clear? So for infinite length, the magnetic field at point P, which is perpendicular distance r, that is B equal to mu naught I by 2 pi d or mu naught I by 2 pi r for infinite length. Clear? If for finite length, what is the magnetic field? For finite length, we have to find magnetic field strength at point P by using ampere circuital law, not by using Biot-Savart law. We have to use ampere circuital law to find magnetic field strength at point P due to a finite length. So for finite length, first at this point we have to draw a amperian loop, and the loop which is passing through the point P. Clear? Because we know if this is the direction of flow of current, if this is the direction of flow of current, if this point is P and this distance is r. Clear? This distance is r and this point is P. We have to find magnetic field at this point. Well, you know, this is the direction of current, then magnetic lines in this way, and these are made concentric circle. Clear? So this is the direction of magnetic field, because it is the direction of current, and in that point the magnetic field which is inward direction, and this point the magnetic field which is outward direction. Clear? This is the direction of magnetic field. This point which is inward direction, and this is the distance r, and this point is the magnetic field which is outward direction. Clear? First, to use the ampere circuital law, we have to first draw a Ampere's loop. Ampere's loop means Ampere's loop which is passing through the point. It's the direction of magnetic field which is inward direction. So we have to draw a Amperian loop in this way, which over the magnetic lines. Clear? And this is the direction of also Amperian loop. Clear? And the direction of magnetic field which is inward direction. Suppose this is the direction of magnetic field which is inward direction, this point inward direction, but this point which is outward direction. And we have to draw a Amperian loop along the magnetic lines. Clear? And this point the direction of magnetic field, and this point the length element which is in this direction. Clear? So angle between magnetic field and DL element along the same line, and angle between them is 0 degree. But this point, this is the direction of magnetic field, and this is the direction of length element, small element DL, because this is Amperian loop in this way. So here also angle 0 degree. If you choose this point, this is the direction of magnetic field, this is the direction of a DL element, so here also angle 0 degree. So if we choose a small element, it is DL, and this is the direction of magnetic field which is inward direction, that means here theta equal to 0 degree. Clear? So we can use Ampere's cycle law, that is B dot dl over closed integral equal to mu naught I enclosed. First, B dot dl, the angle between B dot dl is 0 degree, and here also the angle between B dot dl 0 degree, and here the angle between B dot dl also 0 degree. We can write that is B, which is constant quantity, and here we have to find magnetic field by using Ampere's cycle law for finite length. That is B into dl. Sorry, we can write B dl cos 0 degree over closed integral equal to mu naught within what is enclosed within the Amperian loop. This is Amperian loop of radius r. So within the Amperian loop, the total current which is I, because this is the total current which is flowing through the Amperian loop. We can write it is I. Clear? It is B is constant quantity, cos theta equal to 0. Sorry, cos 0 equal to 1. So we can write B dl closed integral equal to mu naught I, which is equal to B constant quantity dl. dl total circumference, so we can write 0 to 2 pi r equal to mu naught times I, and this is the integration of dl which is equal to L, the integration of dl, that is dl that is equal to L. If we use upper limit and lower limit, then B into, we can, this is upper limit, or we can write L, the 0 to 2 pi r equal to mu naught I, which is equal to, first we have to use upper limit, then B into 2 pi r equal to mu naught equal to I, and B equal to mu naught I by 2 pi r. This is magnetic field strength at point P due to, this is finite length. This is finite length, but this is not the formula of finite length. Why? We know for finite length, magnetic field at this point, it is B equal to mu naught by 4 pi I by D sin phi 1 plus sin phi 2. This is the magnetic field at this point due to infinite. This is not finite, but we derive, this is finite relation. This is not finite relation, this is infinite, but this is finite relation. So this relation is incorrect by using Ampere's cycle law. Clear? So this is incorrect relation, this is incorrect magnetic field strength at point. First, pause the video to give answer where is the mistake, and what is the mistake here. And this is not the magnetic field for finite length. This is the magnetic field for finite length. So the correct statement, the magnetic field, if this is finite length and this distance is r, we have to find magnetic field here. For finite length, this is the direction of flow of current I. For infinite length, this is infinite length, this is infinite length. What is B dot dl? B dl closed integral equal to mu naught times A. What is B? B means B net, total current flowing within the Amperian loop or periphery of the Amperian loop. This is B net. Clear? For infinite length, this length which is infinite. So suppose this is the direction of current and this is also the direction of current in this way. This is the direction of current. For infinite length, this is the direction of current and there is one battery in this way. For infinite. Due to this current element, this is the magnetic field, and due to this current element, here the magnetic field B, which is equal to B net due to this current element and due to this current element, but due to this current element or due to this current, the magnetic field at point P, which is negligible, and due to this current element or due to this current element, the magnetic field which is negligible. Only the magnetic field due to this current element, that is B net. Clear? And B equal to mu naught I by 2 pi d. For infinite, if this length is finite, for finite length, then for finite length, there is a circuit, is the direction of current, and this is positive terminal and this is negative terminal. Clear? If this is positive terminal, the direction of current. So if you find your magnetic field B, what is B? B net due to all the current within the Amperian law and outside the Amperian, so direction of flow of current, direction of flow of current. Clear? In this case, we imagine only this current element, but here this point which is nearer to point P. So that is B dot dl, that is mu naught times I. Here, if we use this relation for finite length, this B is only for this element. We ignore this element, but this current element we cannot ignore, because this point and this point which is nearer, and due to this current element there is most effect in this point. So this is not the magnetic field, this point. Clear? If this is far distance, this is far distance, then this point also far distance, so we can ignore this current element, but we cannot ignore this current element. Clear? So this relation or this law is not valid for finite length. We cannot find magnetic field strength for a finite long straight conductor. This law is only valid for infinite length. So this is limitation. So what are the limitation? Limitation of this law. What are the limitation? This law is not universal. That is, it is not an universal law. This is not an universal law, because we can find magnetic field strength for infinite conductor. We cannot find magnetic field strength due to finite length. Clear? So it is not a universal law. Next point, it is valid for steady current. Steady current only. This is the limitation. Clear? Next point, or this law will go for closed loop for any shape and size. These are the limitations of Ampere-Circuital law. Clear? Now we will go for application of Ampere-Circuital law. So first application, magnetic field strength due to a infinite long cylindrical current carrying conductor or current carrying wire which is solid. So this is the model of a cylindrical wire and which is solid, and this is the direction of flow of current. This is the cylinder which is infinite, and here this is the direction of flow of current. This is the direction of flow of current. Here, due to solid cylinder, total current flowing through the surface and total current also flowing through within the cylinder. Here, this is solid element, and this is the axis of the cylinder, and which is infinite cylinder. This is plus infinite, and here infinite. This is minus infinite, and this is the axis of a solid cylinder. Clear? We have to find magnetic field strength at point A, which is outside the cylinder. And second thing, we have to find magnetic field on the surface of the cylinder. And third point, we have to find magnetic field within the surface or within the cylinder. Clear? So we have to find magnetic field 3 points: outside the surface, on the surface, within the surface. Clear? So first we will go for magnetic field outside, for outside point E. That means here R which is greater than R. What is R? This is axis where we have to find magnetic field strength. This is the distance. Clear? But capital R which indicate the radius of the cylinder. So this is point A, and here we have to find magnetic field strength at point A at a distance R from axis of the cylinder. And this is the direction of current which is I flowing through the cylinder. This is solid cylinder. Clear? Now first we have to draw a Amperian loop, and imagine that this is the direction of flow of current. If this is the direction of flow of current, if this is the direction of flow of current, then it's the direction of magnetic field. This is the direction of magnetic field in this way. This is the magnetic lines in this way. So we have to choose a Amperian loop which is symmetry of the magnetic lines. Suppose we have take or we have choose a Amperian loop in this way, and this Amperian loop which is passing through point A. So first we have to draw a Amperian loop, and this is the Amperian loop. Clear? This is Amperian loop. Suppose this point, if this is the direction of current, then this is the direction of magnetic field. So magnetic field at this point which is inward direction, and current element or DL element, suppose we choose a length element DL which is also inward direction. Clear? And here theta equal to 0 degree. And if we choose another point here, then this point magnetic field which is outer direction, and DL length element which is outer direction, and here also theta equal to 0 degree. That means theta each and every point on the, this is Amperian loop, theta each and every point on the Amperian loop is constant, and magnetic field also on the Amperian loop each and every point is constant, because this length is R, and this length is R, and this length also R, and this length also R, and this length also R. Clear? So according to Ampere's sector law, we can write that is B dot dl over closed integral which is equal to mu enclosed or mu naught times total current enclosed the Amperian loop. This is Amperian loop, so total current within the loop which is I. So we can write that is mu naught times I. Next, B dot dl which is equal to B dl cos theta, but theta here 0 degree each and every point on the surface of on the Amperian loop. So you can write B dl cos 0, that is B is constant quantity, so you can take it is dl which is equal to mu naught I. And what is dl? 0 to 2 pi r, because this is r and the circumference which is equal to 2 pi r. So B into the integration of dl, that is L 0 to 2 pi r which is equal to mu naught I. And if we use upper limit first, then this quantity or this relation turn to B into, this is 2 pi r, so you can write 2 pi r equal to mu naught I. This is mu naught I. So B equal to mu naught I by B equal to mu naught I by 2 pi r. Clear? Just like a infinite long state conductor, and this point the magnetic field B equal to mu naught I by 2 pi r. This is outside point, and in this point the magnetic field which is inward direction, and this one the magnetic field which is outward direction. Clear? This is all about how to find magnetic field strength for a solid cylinder at outside point. Now we will go on the surface of a cylindrical coil. Clear? Now we have to find magnetic field on the surface of a cylinder. This is the surface of a cylinder at point B. So second point, on the surface, that is point B. We have to find magnetic field at point B on the surface of cylinder. Clear? So in this case we have to draw a imaginary amperian loop which is over the and which is coincide with the surface of the cylinder. Clear? And this point, this distance is r. As we know, for the outside point, the magnetic field, that is B equal to mu naught I by 2 pi r. But here it is r equal to capital R. So magnetic field at point B or on the surface of a cylinder, current carrying cylinder, it is B equal to mu naught I by 2 pi. Here small r and this is capital R. Clear? This is outside point. This is for outside. This is on the surface, which is equal to mu naught I by 2 pi r. Clear? Now we have to find magnetic field strength inside the surface or inside the cylinder. Suppose there is a point A, B and point C. We have to find magnetic field at point C, the point C which is within the cylinder. Clear? Now this distance is r. This distance is r. Suppose small r. Clear? Because the distance always measure from its axis. So first we have to draw a amperian loop, and this is amperian loop. First we have to draw a amperian loop of radius r. Last point or third point inside the cylinder or at point C. We have to find magnetic field strength at point C by using ampere circular law, and the point C which is within the surface, that means inside the cylindrical surface. Clear? First we have to draw a amperian loop which is passing through the point C with radius small r. That means here small r which is less than capital R. Clear? In this point. So now we have to use ampere circular law, that is B dot dl over closed integral equal to mu naught times I enclosed. What is I enclosed? I enclosed means total current within the amperian loop. Here total current within the amperian loop, which is not, this is total current I, total surface for the inside, and this is total I within the surface, but this is point C which is inside. So total current I which is not flowing within the surface. This is the current which is within the surface, and this current which is, imagine I dash which is not equal to I current flowing through total area, but total area equal to, which is equal to pi r square. But this I dash current which is flowing through this area, and this area, this is small area, and this area small r, radius small r, so its area, that is a dash, which is equal to pi small r square. This I current flowing through this area pi r square, but this I dash current which is flowing through this pi r square. So first we have to find this I dash current which is in terms of I, because which is I enclosed, that means within the amperian loop the current flowing through I dash which is this direction. This is the direction of amperian loop. Clear? So if we choose here a small point, then this is the direction of magnetic field and this is the direction of amperian loop. So each and every point theta is same and theta equal to 0 degree, because the direction of magnetic field and the direction of length dl element is 0 degree. So you can use, that is B dot dl which is equal to B dl cos 0 degree close integral equal to mu naught into I enclosed, equation 1. First we have to find what is I enclosed. So here I enclosed equal to I dash. I enclosed equal to I dash, because this is Gaussian amperian law and current flowing through the ampere law which is I dash. First we have to find the value of I dash. Now This is total surface area, and for total surface area current flowing through I. That means for total area of cross section, that is total area of cross section pi r square, and current flowing through the cross section, that is I. Total cross sectional area current flowing through I, that is for unit cross sectional area, for unit cross sectional area, which is equal to I by pi r square, and this quantity is known as current density. You know what is current density? That means current flowing through unit area. That means 1 unit area current flowing through I by pi r square. For 2 unit area, current, that is I by pi r square into 2. For 3 unit area, I by pi r square into 3. Similarly, for pi r square, because this area which is small r, which is radius small r, and this area pi r square. So for pi r square area, cross sectional area, the current flowing through this cross sectional area, which is equal to I by pi r square into pi r square. Clear? So current, and this can be right, that is I dash. So I dash is the current which is flowing within the Amperian loop of radius small r, that is pi r square. So I dash equal to I by pi r square into pi r square. 1 pi cancel, so we can write that is pi r square, sorry, I small r square divided by capital R square. This is the current which is flowing through the Gaussian surface, the Amperian surface, and the surface which is inside the cylinder. Clear? So now we have to use this relation here. I dash equal to I by pi r square, 1 pi cancel, so I r square by I r square. So if we use this relation here, we can write which is equal to mu naught into I dash equal to I r square by capital R square, and B dl cos theta, cos 0 equal to 1, this value equal to 1, and B is constant quantity, so we can write dl which is 0 to 2 pi small r, which is 0 to 2 pi small r, that is 2 pi r. So B into element L, then 0 to 2 pi r equal to mu naught times I r square by I r square, and B into 2 pi r, which is equal to mu naught I r square by capital R square. Clear? Now the above relation turn to B, which is equal to B, that is B equal to mu naught by 2 pi r into I r square, so I r square by capital R square. Clear? So 1 r cancel, so B equal to mu naught I by 2 pi, mu naught I by 2 pi, mu naught I by 2 pi by r square into r. This is the magnetic field strength within the surface, that means inside the surface. This is inside the surface. Clear? So from this relation we conclude that is magnetic field for outside point is B equal to mu naught I by 2 pi r. Clear? B equal to mu naught I by 2 pi r on the surface of the cylinder, that is B equal to mu naught I by 2 pi, and this R will be capital R. That means outside point, that is R equal to R, but here on the surface R equal to R, and inside point, inside within the surface or inside, that is R which is less than capital R in this point, B equal to mu naught I which is divided by pi R square into R. Clear? From this relation here, that is B, and this is constant, mu naught constant, I constant, 2 constant, pi constant, but R is variable, because if this is cylindrical element, this is axis, then this point is R, this point A, and this point is this point B, then R also decrease. So here R is variable, so you can write B inversely proportional to R. That means if we decrease the length of the, if we decrease this length, then magnetic field also increase. If we decrease this length, then magnetic field strength increase. If we increase this length, then magnetic field decrease. But this point, the magnetic field is constant, because mu constant, I constant, 2 constant, pi constant, R constant. So this point, magnetic field is constant. This point, and this point, total circumference, the magnetic field which is constant quantity. Clear? This is constant quantity, and this point magnetic field strength is maximum. Clear? On the surface of a cylinder. Come to this last point is constant. This is constant quantity. 2 pi R square also constant quantity for this relation. But here small r means within the surface, and this distance R for last case. So in this case B is directly proportional to R. What does it mean? If this is axis and this point is within the surface, if we take this point on the axis, then R will be 0. If this point take on the axis, then R will be 0. So magnetic field strength on the axis of a cylinder will be 0. If we increase this length, then magnetic field also increase, because B is directly proportional to R. If we increase length, then magnetic field also increase. If we increase and come to and reaches the point on the surface, then magnetic field which is equal to mu naught I by 2 pi R, and which is maximum. That means if we come from axis to on the surface, then magnetic field increase. But after the surface, if we come after the surface, that means outside surface, then magnetic field decrease. So if we draw a graph by using this relation, then the graph will be like this. Graph, this is distance, and this is magnetic field strength. Graph versus magnetic field versus R, distance graph. Clear? Now look at this relation, and first inside point. Clear? B equal to B is directly proportional to R. That means if we take, this is cylinder, this is axis, inside point, this is R, this is on the R surface, and this point is R, outside point. Clear? But inside the point, inside the surface, magnetic field which is directly proportional to R up to outside surface. That means here magnetic field increase and stop. That means here constant. That means magnetic field increase from the axis of the cylinder to on the surface. Then magnetic field decrease. So magnetic field increase, that is B directly proportional to I. So B directly proportional to R, because here R, and this point, it is R equal to capital R. That is, this is inside, and this point is known as on the surface. Clear? Because on the surface, the strength of magnetic field which is maximum. This is on the surface, when R small r equal to capital R. But if we come from the outside point, then magnetic field is inversely proportional. Then this is like this. This is outside point where B is inversely proportional to R. This is graph, and graphical representation of magnetic field strength due to a solid cylinder. For hollow cylinder, suppose we have a hollow cylinder which is infinite and current flowing current flowing through the surface, not within, current flowing over the surface which is I. That means this is direction of current and current flowing through over the surface of a hollow cylinder. Clear? There is also 3 point A which is outside point, first point which is outside, that means R which is greater than R, and this point R, this is the radius of the cylinder, hollow cylinder, and this point we have to find magnetic field. Then we have to first draw a imaginary Ampere's law, Amperian law, and total current within the law which is I. The same thing for solid, that is B equal to mu naught I by 2 pi R. Here also, that is B is inversely proportional to R. B is inversely proportional to 1 by R. Clear? Same thing as you discussed previous, that is for a solid cylinder, similar case. So next on the surface of cylinder, that means on the surface, if you draw a imaginary, then this is on the surface, if you draw a imaginary Amperian law, then total current flowing, this is within the surface, then total current flowing over the surface which is current I, and in this case the B equal, we can get B equal to mu naught I by 2 pi capital R. Same thing as solid case, but inside the surface, inside point, this is outside on the surface which is R equal to R, but inside R. Suppose we have to find magnetic field strength at this point. Suppose this point C, which is at a distance R within the hollow cylinder. Clear? This is a hollow cylinder and this is the circumference or area, or this is the surface. In this case, for hollow cylinder, total current flowing through over the surface. This case and this direction, this is the direction of flowing of current. But inside the conductor, inside the hollow cylindrical conductor, there is no current because total current flowing over the surface. If we choose a point here within the hollow cylinder, then first we have to draw a Amperian law. This is Amperian law, and this is the radius which is equal to pi r square. Clear? But within this area there is no current because total current which is flowing over the surface, but inside the surface there is no current. That means if we use Ampere's law, then we can write for this case, that is B dot dl over closed integral, that is mu naught times I enclosed. I enclosed means here there is no current because this point we see which is inside the hollow cylinder, so I equal to 0. If I equal to 0, then magnetic field inside the surface equal to 0, so B equal to 0. That means magnetic field inside the surface of a hollow infinite current carrying cylinder which is equal to 0. Here there is 3 point also, point 1, point 2 and point 3. Inside the hollow cylinder, magnetic field strength is 0, but outside the point mu naught I by 2 pi r which is equal to solid cylinder. But if this is on the surface, this is outside point which is equal to mu naught I by 2 pi r which is equal to the solid cylinder. If you draw a graph magnetic field versus distance, then magnetic field versus R, this is x-axis and y-axis. If we choose the distance along x-axis and along y-axis, we have to take magnetic field. Clear? But this is the axis. On the axis, magnetic field is 0. If we increase the length from axis up to surface of the hollow cylinder, then magnetic field strength also 0. That means here magnetic field, if we increase the distance up to r equal to r, if we increase the distance up to here r equal to r, then magnetic field strength is 0. And this is the magnetic field strength. Here magnetic field strength is 0. Next, then if we increase the distance after the surface of the cell is a hollow cylinder, then magnetic field strength is decreased. That means B is inversely proportional, because B is inversely proportional to 1 by R. This is outside point. B is constant quantity. B is constant quantity. B is constant or maximum on surface, and B equal to 0 inside. So it will take another point which is outside is A point, then magnetic field strength decrease. This is the graph. Clear? This is outside. This point is on the surface, and this point inside. Clear? And this point magnetic field is maximum. So from this graph we conclude that magnetic field strength within a hollow cylindrical current carrying wire is 0. Here magnetic field is equal to 0. But on the surface, magnetic field strength is maximum, which is equal to the magnetic field strength like solid cylinder. But outside the surface, magnetic field strength is decreasing. Clear? This is all about how to calculate magnetic field strength for a hollow and solid infinite long state conductor.